Let's dive right in. This video is both a tutorial and walkthrough for the periodic table geonodes I've created. There are timestamps below for those who want to skip ahead, and this video is going to be very technical, so if you want to skip to just the walkthrough on using the periodic table, check the timestamps. With that said, let's get going. Welcome to part 2 of Advanced Geometry Nodes. In part 1, linked in the description, we looked at creating and using variables in a fully procedural network, using the example of graphene sheets. That was largely based on working with a mesh generated entirely in Blender. In this video, we're going to look at how to store and use external data. We'll cover aspects of customizing an object using geometry nodes and shader nodes together. We'll talk about some design choices for larger assets based on features of geometry nodes and some future considerations for better design. From there, we'll go through how to set up specific selections, animations, etc. using simple math. And finally, we'll close out with a breakdown of how I created atoms to place on top of each element, as you can see here. Note that everything in this video is going to rely on the periodic table nodes that I've released. As always, my assets are available for free with a CC0 or public domain license. In an ideal and possibly future system, we'll be able to read data directly from a spreadsheet into geometry nodes. For now, we can store external data using copies of our main object. Each copy will have the same number of points in the same order, identified by an index or a vert. Using the index will let us transfer information from the copy to the main object. To create the table, I made 118 points that I spread out over an imported image of the periodic table. No edges or faces, just points. This makes it faster for Blender to run. Importantly, each point was created in order. So hydrogen is on point 1, helium is on 2, lithium is on 3, beryllium on 4, etc., etc. In geometry nodes, each point, or vertex, has an index, starting from 0. We can see that if we come to the geometry node spreadsheet editor, and here are our points, 0, 1, 2, 3, etc. By making sure that each element is associated with an index, we can easily keep track of the information that we are storing in the copies. Let's start with creating the atomic number variable since we don't require a copy. In the geometry node spreadsheet, we can see the index on the left, starting at 0 going to 117. To create the atomic number, we simply need to add 1 to this so that it goes from 1 to 118. In fact, if we scroll all the way along our spreadsheet, you can see the atomic number in the far column. Very simply, all we have to do this is move past this giant network of nodes, come to the variable section, open this up, and you can see we're taking our geometry in, grabbing the index, adding a value of 1, and storing that in the named attribute atomic number. You may have noticed that geometry nodes only lets you store numerical data. So how can I import another number, such as the atomic weight? To start, I need a copy of the 118 points that make up the table. I've included a data object in the periodic table values collection, and to access that you have to enable a collection and then also make it so that you can select it and see it. Once it is selectable, which you can toggle with this arrow, you can grab the object and this will give you a copy of the 118 points. If I want to add a new piece of data, I would Shift-E to duplicate this, right-click to snap it back in place, and you can see I have my data template object, which we'll rename example. Now, the indices in this object are the same as the ones in the actual periodic table, i.e. they go from 0 to 117. What this one has, though, is a series of different values that I can use to store numbers, specifically in the X, Y, and Z positions. So if I tab into edit mode, Alt-A to deselect everything, and let's say I want to grab the position right over hydrogen. I can see that this has X and Y values that I don't want to touch because it keeps it positioned over the atom that I want to work on, or the element rather. But I can change this Z value, and so I could give it the value of the atomic weight of hydrogen, namely 1.008. Going through, I could do that for every single value in the table, and then I just have to import it into my main object. So we'll tab back into object mode, select our periodic table. These are the geometry nodes for that. And what I want to note here is that I'm creating all of these variables before I actually build the table itself. That's because I want all of this information to be assigned to the individual points before I start manipulating those points. And so to do that, very simply, all I have to do is bring my data template object in, so I drag it in, and now I'm going to use a attribute, transfer node. I'm going to set this to index, so that index 0 is going to be the same in the template object and in the original object. 1 will match to 1, 2 to 2, etc., etc. Then I can bring the geometry that I just imported in as the source, and I can choose an attribute that I want to transfer into my geometry. So in this case, I want to transfer the z location. So to do that, drag out, create a separate xyz, and then I'm going to drag z into this attribute. I can now use this value in my original table. And so you'll notice that there are a number of data objects here. So if I go ahead and zoom in, I'm actually pulling the z value out of each of these. For the first one, I pull the x, y, and z out because I use the group and row data, so it makes sense to still use x and y. But for the year discovered, for instance, every single element has a z value that corresponds to its year discovered. So 1910 or 2002, etc., etc. I transfer that z position, which is the year it was discovered. I map it through the index. I round the number out just so that it's a little cleaner to work with. And I plug that into a store named attribute. I name that the year discovered. And now this is in the main object geometry. So the periodic table contains the year discovered, which you can see right here in the spreadsheet. We could use the x and y positions as well to store other pieces of data and simply separate out those values. The index is the same regardless of the position. I like to use just z because it kind of cuts down on the ambiguity and I can assign each value from a top-down view. So I simply come in, I grab lithium, I tab into edit mode, and then I change the z value. It makes it nice and easy. You could also write a Python script to pull this data in from a CSV file, and then it might make more sense to use x, y, and z. In that case, you could actually use fewer objects to store more data. With this approach, every time I want to add a new piece of data, I simply duplicate the data object, rename it, and then add the z values appropriate. For some labels, such as classification, I've just assigned a number value to each option. So for instance, the alkali metals are all set to a value of 1. Noble gases are all set to a value of 6, and the corresponding data object has each element in that group with a z value that matches. You can use this to create custom selections as well. Say I'm working on a particular synthetic route, and I only want to highlight certain elements, particularly the ones that I've used in the synthesis. All I would do is create a data object, set the z values for each of those elements to 1, and leave the rest 0. This would give me a nice binary selection. You can see in the geometry node spreadsheet that I've included a fair number of parameters in the periodic table, including the atomic radius, electron affinity, which block it belongs to, what group it's in, what row it's in, what the electronegativity, ionization energy, electronegativity, year discovered were. I will likely add a few more to this, and these will be updated in the asset as I go. So if you have ideas for what would be useful information, please feel free to throw it into the comments. So at this point, we've got our rationale for importing and using data. We know that it works because we're matching the indices of our main object with our data objects. So how do we use this, and how did I build the periodic table? Before getting into that, I want to note that this approach was borrowed essentially from Brady Johnston's molecular nodes. It is a fantastic demonstration of the real limits of this technique, and if you want to go check that out, I strongly encourage doing so. I've linked a number of videos. Big thanks to Brady for really developing this in a way because it has made it possible to do these things in lieu of some of the systems that we hope will be coming to Blender in the future. It's very clever and worth taking the time to acknowledge. Very simply, the table works by creating each of the 118 elements using a common elements node, which you can see here. These nodes generate the tile and the frame. They also hold the essential information displayed on the element, such as the abbreviation, the name, the atomic number, and the atomic weight. All of this information is explicitly coded into the tile, and that made sense because it's used to build and display those rather than pulling them from data objects and having to worry about manipulation. In the actual table itself, we have all 118 of these, and they're arranged so that each one has a color for the actual node based on the row, and the groups are all assigned colors in frame for the columns so that you have a bit of an easier time navigating it if you want to go in and change something specifically. Let's take a second to look at a specific element node. We're going to come in to hydrogen. So if I come inside and I click the actual little icon at the top here, this opens the internal section of the node, and you can see what everything is doing. So if we go to the top, this is generating the frame. Specifically this part right here, this quadrilateral curve, is generating the actual border. And if I wanted to swap out for a different type of profile curve, then I could give the border a different shape entirely. I could make it a star, for instance, or a tube. Now, more interestingly, if we come down here, this is where there's a second node called element controls. And if I click inside here, then I have the capacity to change things such as the font. So if I wanted to, I could change the font, and if I were to change it in any one of these nodes, it would update it for all of them. So we'll zoom in here and keep in mind that right now we're in the hydrogen node. I'm very simply going to click, going to grab a new font, something that is obviously very different right here. And you can see that now all of the atomic weights have changed to this new font, Berlin Sans FB Bold. And so I'm just going to quickly undo that. But let's say hypothetically that I knew I wanted to change one of the elements for essentially the entirety of my work with this, and I need it to be different from all the others. In that case, I'm going to have to come all the way back out and find the element I want. Let's say cadmium. So I'm going to come across, I'm going to come down. Cadmium should be in red. It should be right near the end. Here it is. And of course, all of the nodes are labeled so that you can find them relatively easily. And in this case, to make sure that I'm only changing the one, I have to click this little icon right here. Now cadmium is pulling its own data entirely. And I'm going to come in and I'm going to click this one as well. So make sure that we click here. This now has its own controls. And if I come in and change the font again, we'll go for, again, something a little bit obviously different. Right there, perfect. Now the weight of cadmium has changed, but all the other elements are the same. And so that's important because if you want to make these big sweeping changes, you're going to have to do it by making the elements either, well, if you want to make big sweeping changes, then all the elements are connected and so they'll all update at once. If you want to change them individually, you'll have to separate the nodes out by clicking on the little icons. And so if we come back now, you can see only 117 of the elements are actually using this base core elements node, and now the cadmium one is using a different version. So that's very important. So we undo all that, and then if we actually go over to the side here, you'll notice an absolutely massive number of connecting noodles. So basically 118 for every single parameter. You can count the number of parameters, all of these hooked up manually. Now, if you wanted to change some aspect of the whole network, then it is easiest to do that through the modifier panel, and all of the core attributes have actually been exposed here. So if I wanted to change something such as the size of the number, then I can bring that up. It's going to grow, bring that back down. And then similarly, I can control the offset, I can control the arrangement. So if instead I wanted the name to be up here and the abbreviation to be smaller and underneath, I could make those changes. You can also assign all of the materials for things such as the state text. So in this version of the table, it actually has the whether or not it's a gas or liquid or solid at room temperature built in, and that is the state text material, as opposed to just the regular abbreviation material, which is the white text that you see up here. But if I want to actually change that, so we'll grab the number material here, and we'll change it to the state text material, then that will update there. And similarly, I could do the same thing for the weight material, state text, and that would update. So now all of these have those properties for red. And these are all built in. This works through the shader nodes, and we'll get into that a little bit later. From here, all the elements that we see with the tiles and that are all connected so you can control everything all at once are placed as instances on one of these specific 118 points using the series of nodes up here. The reason that I did this is that instances let you manipulate the whole tile as though it were a single object. So if I want to scale or rotate, I can do it to everything all at once on the 118 points, instead of having to modify all the extra geometry needed to create the letters, the frames, the tiles. I've also added controls for that, and we can see the difference right here. So if I come down and go to rotate table, I'll go ahead and I'll rotate the whole table by 45 degrees. Now this is rotating the 118 points, and everything is going to maintain the alignment. However, let's say that I want to rotate the individual tiles by 45 degrees. So we'll come in, we'll grab rotate elements, and I'll rotate the tiles by 45 degrees. Now every single tile is rotating, and so I can combine both of these controls at once, or have them entirely separately, and the same is true of the scale. The major limitation of the instances approach right now is that it recalculates the entire table anytime a change is made, and that brings me to an exciting future possibility. Caching is something that has been discussed by some members of the Blender community. The rough idea is that you could select a node, or a whole group of nodes, in this case the element generation, and essentially tell Blender, calculate this once. For instance, if I'm happy with the size of my frame and my text and all the aspects of my nodes, I could simply cache the element creation. And then, instead of calculating the whole thing every time, it would just do whatever manipulations I wanted. And so right now I have it enabled so that if I come down to the bottom here, you can see in the frames how much time it takes to do every manipulation here. And so creation of all the elements takes 428 milliseconds. If I go over to the side here, you can see the whole table, instancing and manipulation and everything, is 486. And so a very significant portion of that time is just dedicated to creating the table. And so if I can tell Blender, only calculate this once, then that means that I'll be able to do all kinds of animations and manipulations, et cetera, much, much faster, almost in real time. And so that's hopefully something that we'll be able to integrate going further or going forward. And if it is, then I will certainly update the table in that regard. A bit of a quick note on something that I would probably change if I were doing this again, and that I will likely implement in the future. As it stands right now, every time that I've added more data to this table, I duplicate the underlying 118 points, and I add in the data manually in the z-axis. Going forward, I will very likely just build in some sort of small Python script to this file that lets you pull that information from a CSV. It'll mean that you can use fewer objects to store more data, and it will likely speed the process up considerably. I'd like to have that degree of customizability, so I will likely integrate that. It's something I think is worthwhile. Really, I designed this from a teaching and readability point of view, and so that's why it has worked out the way it has so far. I do want to briefly touch on a significantly more advanced subject for how I could have built this table instead of the way I did. So right now I'm using other objects, and that is sort of, as I mentioned, the way that Brady Johnson created molecular nodes. What I could have done instead, because I have a fixed number of 118 points, is I could have simply duplicated all 118 points for every single piece of data that I wanted to add. I would duplicate the points, and then I would use a modulo of the index value. So as soon as I get to 118 here, the next point over is going to be 119. If I take the modulo of that, it drops back to 1, and then 2, 3, 4, 5. And I could do that every single time I want to add a new piece of data. And using the same idea of storing data in the X, Y, and Z positions, I could do that. The benefit being everything would be contained in a single object instead of in however many data objects you need. I don't think it's quite as friendly to modify, and that is one of the reasons I didn't use that approach. It's also a little bit more advanced and requires some understanding of attribute transfer. For a better explanation of this concept, I will link a video from Arendelle on that subject. As it stands right now, this is a pretty friendly and easy to work with piece of kit, and going forward, I hope to sort of expand on that either through the addition of more data myself or through the creation of tools that will make it easier for end users to do that themselves. Let's go through how to modify the table. To do that, I'll cover a few examples. The table has a number of user-facing controls in the modifier stack. Text resolution never really needs to exceed 3, and dropping it down to 1 will make everything much smoother and faster. The text and border height are fairly self-explanatory, as is border width. Smooth will enable smooth shading on the whole table, which can be combined with the bevel modifier to create nicer edges. This is significantly slower though. The frame, frame border, and no frame options allow you to toggle between different appearances. They also automatically adjust the text height to match each case. By default, this is set to framed border, but if we bring this value down to 0, and then bring the frame value up to 1, you can see now we have a simple frame, and the text actually dropped down at the same time. So if I go ahead and make the frame hidden again, we have the tile, and if we want, we can have the border come back, and of course if we want to, we could override all of that by simply having no frame whatsoever, and then it would just be the text information. In the version released as of this video, you can separately control the materials for every single part of the information presented on the tiles. So that includes separating the tile and frame material, and the materials that are being used to convey the abbreviation, the name, the atomic weight, and the atomic number. Each of those has its own material control, and you can customize those. Moving further down, we have controls for the whole table for translating in X, Y, or Z. Similarly, we have controls for rotating and scaling the whole table. So if we zoom out and change some of these things, let's move the table 1 meter over in the X direction. And then let's say we want to rotate 45 degrees in Z, and we'll scale the whole thing by 2 times in X and Y by grabbing those and entering 2. So this is going to spread everything out. because we're actually just scaling the original points, but we're keeping the tiles the same size. If I wanted to then come down and scale the individual tiles, I could do that through scale elements. And in fact, let's go ahead and do that now. Grab these, set them to 2. And so now I've matched the scale there. And note that I did not change the z-scale. We can also do rotation of the individual elements as I showed before, so let's go ahead and rotate the y by 45 degrees. And all of them are now slanting into the floor. Finally, the last sets of controls at the bottom are for placement and size of the text that is shown on each tile. So if I want to, I could rearrange everything through here, and I'll quickly cut to just a different version or presentation of this information. And here you can see that by changing these values, I've rearranged the tiles to have a different display of the same information. Below the user-facing controls is a list of all the data and the variable names assigned to them. These are the variables needed to use the data both in geometry nodes and for materials with shader nodes. Note that these are case sensitive, and we'll cover them in some of the upcoming examples. I will add more data and selections in future versions, and possibly by request if there is a specific case you have in mind. As it stands, the table is compatible with Blender's asset browser. Blender will import objects that are used in a node tree, whether or not they are marked as assets, so all the data objects are preserved. It also imports their render properties, so all the points will appear, but they won't show up in your renders. Simply drag and drop from your own asset library into the scene. From here, I like to open the side menu in the outliner, grab all the data objects by holding down Shift and then selecting to the bottom of the list, hitting M and moving them into a new collection. And then you can simply hide this collection by hitting the check mark, but you'll notice that none of these have the camera icon, so they will not appear in your renders. And this is a nice way to clean it up if you want to use the periodic table in a different Blender scene and not have to work from the asset file. Let's start modifying the table with a simple example in geometry nodes. Come to the geonodes tab and find the area that says modify table here. If we zoom out, you can see this is the table generation, and modify table here is placed right between these 2 points. We're going to make the node height, or essentially the element height, a function of the first ionization energy. Then we'll also add in a feature that raises up nodes discovered within 10 years of 1900. We'll start by adding a scale instances node and connecting it between these 2 points. From there, I'm going to add an input named attribute. And I'm going to choose the ionization energy. I'll move this over, drag this out, and connect this into a combine XYZ. And I'm going to specifically plug this into the Z socket. I'll make sure that X and Y are both set to 1. And then I'll connect this vector output into the scale. While this is quite visually compelling, these are a little bit oversized. This is because the ionization energies cover a huge range of values. We can visualize that range of values using a handy tool that I've added in below. So we'll come down here, and we're going to simply choose our first ionization energy. We'll plug the minimum into the value here, and if we come to the viewer, we can see that the minimum ionization energy value is 0. This is a placeholder for where there's no data. If we take the maximum and plug that in, you can see that the maximum value is 2,372. So what we're going to do is we're going to scale our values of ionization energy to a more reasonable range. Let's say instead of going from 0 to 2,372, we'll instead remap that from 1 to 100. To do that, we're going to move back to our instances node right here. And between the attribute and the combine XYZ, we'll drag out a map range. And we're going to have this go from 0 to 2372 and output a value from 1 to 100. We'll connect this into the combine XYZ, And you can see everything now shrinks down to a much more readable scale. From here, I'm going to make a few small changes. To start, I'm going to get rid of the framed border because in this case, I think having just the frame looks cleaner. You'll also notice that the text is being scaled to match, so I'm going to bring the text height down from 5 to 1. One last thing that I'd like to do is correct for the elements between 104 and 119. These are all essentially flat. They have no value, essentially 0, because there's no data available for any of them. And so what I'd like to do is make sure that I'm not actually going to scale those ones. In some cases, when you render this out, these might intersect with the tile. The text, that is, will intersect with the tile, and it can look a little bit off. To do that, we're very simply going to drag out from the attribute, create a greater than. Essentially what this says is that only elements with a ionization energy greater than 0 are going to be scaled. So we'll connect that into our selection, and now this bottom row of elements will not have the text intersecting issue. Now we're going to pick out all the elements that were discovered within 10 years of 1900, and we're going to raise them up. If I tried to translate those elements or move them up after the scale, they would go up by a relative amount based on how they're scaled. So they'll shoot up much higher than I want them to. I'd like them all to move up at a uniform amount, and so I'm going to make sure to do the translation before the scale. So we're going to come back in the nodes. I'll add in a instances, translate, put this in right here. And then we're going to do the same thing for the selection. So I'm going to move every element up by 5 meters. Let's see, they're all going up. And now for the selection, I'm going to drag out to create a compare equal. And what I'd like is for a float value, an integer is fine as well, but we're going to use a float value that is equal to 1900. In fact, specifically, we're going to use the first input for the actual date. So the B socket will be 1900. The epsilon value will be 10. And we're going to input our attribute in here. So again, input, named attribute, we'll grab the year discovered. We'll place that in right here into A. And now only the elements that were discovered within 10 years of 1900 have been elevated above, while preserving their increased scale based on their first ionization energy. This is a particularly useful tool for discovering things about when the elements were discovered. So if I wanted to, I could go and say, tell me any element that was discovered in sort of a more ancient period historically. So let's go ahead, say less than, and I want every element that was discovered before 0 BCE. And here they all are. Unsurprisingly, most of these are metals, or things like carbon. And again, if you wanted to actually check the year, or the range of years present in the elements, then we would come down, we'd change this to year discovered, and then we could see in our viewer here that the most recently discovered element was in 2009, and the first discovered element in this table is in 9000. And so just going negative, I use those as sort of before common era numbers. And I believe that the single instance here is copper. The thing that I really want to drive home here is that anytime that you're going to do a scaling operation, you usually want it to be last, especially if you're trying to scale the whole table. Because of the way that Blender works, if you do scaling first, it will have a consequent impact down the line on things like translation or further scaling or rotation. So any full table scaling should happen last, and you should make sure that you're only targeting the elements that you want to for that effect. I'd like to use a worked example to emphasize some of the aspects of working with animation specifically surrounding scale. Let's go ahead, press play, and see what we have here. All the elements are going to fade away to 0, or essentially nothing, except for these 4 halogens, which are then going to change their height based on the electronegativity. And this is the type of thing I could imagine people doing with this table, choosing a very specific selection of elements and then modifying some aspect of them based on a property. Let's go over to geometry nodes and see how this is actually playing out. Now, there's a series of nodes down here that is actually controlling this effect, but first I want to clear up one key misconception, which is this idea that you could maybe change the scale and then change it back somewhere else. Let's connect the original table, and we'll reset our animation back to the beginning. If I were to come in and change all of the elements to have a scale of 0 right away, so we'll connect this up, and you can see everything is gone. But let's say I want to choose just those 4 halogens I had before. This is a series of nodes. Choosing them, we'll break that down in a second. And then I say scale those back up to a value of 1. If I connect this, you can see we still have nothing. And that's because scale multiplies. It does not add. So I can't go all the way down to 0 and then come back to 1. It's just not going to play out that way. If I had changed this value to something very small, let's say 0.1, then I can multiply everything up to, say, 10. And it would just bring these ones up. But these are still here. And if I want them to be gone completely, I have to change the way that I'm going to think about this. One thing that's worth noting here is the animation and the geometry nodes do not follow in the same order in time. So in my animation, we hook this back up, I press play again. The elements are fading away first, but that doesn't mean that I have to do that first in my node tree. I can simply control the animation for that later on. If anything, I find it's personally better to do larger scaling operations later in the nodes, because that's going to mean that you have more flexibility earlier on. I don't have to worry about everything else being multiplied by 0 if it's the last thing that the actual node computation looks at, because the nodes will essentially go left to right. And so if this is the last thing that they're looking at, then everything mathematically before here doesn't care about what's happening here. But I can still animate it whenever I want in time for my animation. Let's break down how this is actually working, and maybe that'll clear a little bit of this up. We start by importing a named attribute for the column. We're choosing just column 17, and then for the classification, I added a legend along the side, but I just want the reactive nonmetals. I'm going to say when both of these are true, scale, and I'm going to use that for the selection. Then for the actual scale, I come down here and I'm essentially switching between two values using a mixed RGB node. So you can find that in color, mix RGB. And basically what's happening here is when this value is 0, it will pull data from this top socket. And when it's 1, it'll pull data from this bottom. So the bottom socket is just a scale value of 1, the default value. When this transitions from 0 to 1, or from 1 to 0 in this case, then as soon as it hits 0, it'll start to take information from here. So it'll say, what is the electronegativity value for each of these elements? I'm multiplying that value by 5 and then putting that into the Z scale. The reason I'm multiplying by 5 is just to make it a little bit more obvious. If I made this 1, then it's hard to see. And so essentially the 5 is just to make it more apparent. Then this can be animated however I want, whenever I want in my timeline to control this effect. From here to the very end of the scene, I have another scale instances. And like I said, this one is technically coming after this, but the animation for the keyframes is different. So this animation occurs first. This animation occurs second, but the math is in the flipped order. So I never have to worry about the scaling. In this case, I was very careful because I added a not right here. So what this selection is just those 4 halogens, and then the not means every other point. So in this case, I'm actually scaling down from a value of 1 to 0 for every single thing that is not one of these 4 halogens. But again, it doesn't matter what order the animation occurs in. What matters is the order that geometry nodes executes in. So if you want to manipulate scale, especially if you want to do a fading animation, put it at the end and make sure that you have a very clear selection handle. Because if I want to do anything on this afterwards, translation or scaling or making it more apparent in some capacity, I'm not going to be able to do it after this node. And so this is the node that should be closest to the end of the table. I wanted to include this as a little bonus section on how you can think about rearranging the table. In this case, we're back in the modified table area, but we're using a set position node. We're going to use this to control where the actual elements sit. And what we're doing is we're using a mix RGB to essentially switch between 2 positions. Vectors and colors are interchangeable often. So I'm going to use the original position when this is set to 1, and I'm going to use a different set of positions based on the atomic number when it's set to 0. You can see at the start of the animation, it's 0. And there's also a little value over here, but we're going to break this down from the beginning. I'm going to pull the atomic number, multiply that by 1.1 to add some separation between the tiles. I'm going to input that into the combine XYZ to the X socket to create a vector. The Y value actually here is just moved to position this sort of along the line. And then what this is essentially going to do is that as I go from 0 to 1, it's going to change from the line by line atomic arrangement into the periodic table as we all kind of recognize it. So if I come to a top view here and reset the animation, then press play, you can see very slowly all the elements are going to move into their respective locations. And this is a nice way to visualize aspects of the table based on something else other than kind of how we recognize it. You could do this based on the atomic number, the atomic weight, which I believe is how Mendeleev actually decided many of the initial trends. But you could also do it based on things like which block they belong to, or whether or not it's a reactive nonmetal, transition metal, or something to that effect. And so this is just a convenient and very easy animation setup where you're just going to cycle between two different sets of positions using set position and this mix RGB. It's a very easy way to animate through just this factor, and that's a nice tool to have. Frame customization is very easy. Simply come to the Geometry Nodes tab, move to any of the elements, in this case we'll go with helium, and click on the little icon at the top of the node. From there, we're going to modify the frame creation controls, specifically this profile curve. Right now it's set to a quadrilateral, so if we come in, we zoom in from a side view, you can see we have this nice, essentially rectangle. I'm going to very simply hit Shift-A, add in a primitive curve, and I can add in whatever I want at this point. Let's use a circle. I'll connect this circle in to the profile, and this is going to be comically oversized, so we'll start by bringing the radius down quite considerably. And now you can see that my frame is actually a nice little cylinder instead of the rectangle that I had before. We'll bring this up, make that more obvious. But if we want to, we could swap this out for any number of other simple curve primitives. For instance, after a little tinkering, here is the star profile on all of these. And if we were to come over to the Geometry Nodes tab, there are a few things worth noting. One is that we disconnected the controls for the frame height and width by essentially disconnecting the quadrilateral controls. So you'd have to rehook those if you wanted to be able to use them. And the other thing that's worth noting is that this should still work with all of the frame controls. So if I simply turn frame borders off, they're still going to disappear, and they will come back however you customize them. And it's worth noting that this customizes them for every single element. So very simple control if you want to do some customization of your own periodic table. In this example, we're going to add spheres on top of each element that shows their relative atomic radius. In this case, we don't want to modify the table. In fact, we want to work with the underlying 118 points. If I move down, you can see that I've conveniently added this here with the table positions. So simply drag out from here to create an instance on points. And from the instance, I'm going to drag out again to create a UV sphere. This is comically oversized to start, so I'm going to bring the radius down to 0.1. Then from the instances, I'll drag out to create a join geometry. And I'm going to move this all the way up to the top, connect it to our table output, and use the join so we could see both at once. If I zoom in, you can see we have these little white spheres. Let's go back and start modifying our data. What we need to know for our atomic radius is what the range is, so the lowest and the highest value. It's already conveniently plugged into our tool for checking that, which is just under the table positions. So choose the variable, connect the minimum to the viewer. And you can see that our minimum value is -1, which means there's no data for that value. We actually don't want to even include those, but we're going to use it conveniently in this case. The maximum value is 260, and so that's going to define our range. So very simply, add in a named attribute, choose the atomic radius, and then I'm going to drag out here to create a map range node, and I'm going to say any value from 0 to 260, we're going to remap in a range of 0 to 5. And again, that's just going to give us that nice sense of scale. So Shift-A, add in a scale instances, connect that between here, and then very simply connect this into the scale. And you can see that because all of these values where we have no data, so any of these down here, or these ones down here, because they are essentially being multiplied by 0, they're not appearing at all. That's very convenient. The 0 to 5 range is a pretty nice demonstration of how this is actually all proceeding. So you can see hydrogen has a tiny radius down here, all the way up to some of these that have a much more substantial atomic radius. And that's a very nice way of visualizing this trend. We want to do a few things to clean up. For starters, we're going to move everything up. But like I said before, we want to make sure that we translate first. So I'm going to go ahead, add in a translate instance. And then we're going to move this up by an arbitrary value. In this case, I chose 1. I would like all of these spheres to be shaded smooth, so I'm going to add in a set shade smooth right here. And the last thing I'd like to do is to give them all materials that match their underlying frame. So to do that, we'll add in a set material node, Shift A, set material, put it right there, and I'm very simply going to choose the frame material. Now right away you'll notice that they all have one frame, or one material specifically, one color. And what I'd like to get them to do is adopt the underlying tile color. To do that, I need to move these over. I'm going to add a realize instances node. Put this between the scale and the material, and now they all match perfectly. We come to the top, we can see the relative atomic radius and the trend as you move across. So we have not only our table with all the information, but we have all of these little spheres that are demonstrating some aspect of the data. And you can do this for any number of different things that are coded into the table. The reason that this works is because the shader is actually set up to match the tile, and I'm going to briefly touch on that in the shading nodes. If we look at the frame material and the actual shading nodes, we can see that we can pull in an attribute. And this is one that we created for the geometry nodes. It's the classification. You can see that down here, and it is very important that we follow the case because this is case sensitive. So we import the classification, we use that as a factor, and we route this value from 0 to 9, which is we take this value of classification, which goes from 0 to 9 based on this legend, and we say change that from a value of 0.1 to 0.9. We plug that into the hue socket of a color, specifically pink in this case. And that means that as you go from 0 to 9, you have this nice gradient across and everything is essentially assigned a different color. This is more or less obvious based on a mix with black, so I just did it so that you could have a little bit of control over that gradient. And then this plugs into the base color. This is essentially a regular material. You can also do this for things such as the block. So if I wanted to, I could connect the block instead. So the S block, the D block, the F block, etc. And now they're all separated based on that. And you can see all the spheres updated at the same time. So this is just a convenient little feature. You could do this based on any number of parameters. These are the two that are typically most represented, and so it's what I chose. As an example of setting up shaders, we're going to talk about the cursor that comes by default with the periodic table. If I grab this object up here, hit G and Shift Z to move in just the X and Y plane, and if I drag it over any element, that element is going to glow. You can see that here. If I move along, it'll glow there. Again, through anything and preserving the colors as well, so even though it's a little harder to tell, the red is glowing and the blue is glowing as well. So this is done through primarily the material setup. We're going to shift over to the shader nodes to see how this actually works. In the shader nodes, we can look at either the state text or the text material. In this case, we're going to use the text material because it focuses on just the cursor. We come down here and we see that cursor is actually an attribute that we're reading in, putting this value into a multiply socket, and using that to control the emission strength. So whenever cursor is true, in fact, we can visualize that by holding Control Shift and left click. And you can see that for the state text, everything has gone black except the white on nickel. And that is because nickel is currently set to true. If we grab the cursor and move this over, you'll see that the nickel text fades to black. And as we move on to copper, the copper text for these values becomes white. So essentially, we're pulling a value out of the geometry nodes and using it to control the shaders. Let's head over to geometry nodes and we'll see exactly what cursor is and how it works. In geometry nodes, we can see that unlike the export data, which is contained in this frame and is basically pulling all of the variables out, the cursor is a Boolean value. And if we follow it up and move along, we can see it's actually being decided way back here by this series of nodes. Essentially, we're looking at the distance between two positions. One is the location of this empty, which is the cursor object, and the other is the position value of the individual element. We're looking at the distance, and we're saying where the distance between those is equal to 0 within 0.02, so plus minus that value, then we're going to return true, and everywhere else we're going to return false. If we go further back to check out where this position is coming from, we can see that it's actually before we instance any of the elements to create the grid. So the reason that we are capturing the position attribute back here is because we need to do that before we create the elements. If instead we were to use the position sort of from the actual table after it's all been created, we'll see what happens right now. We'll go ahead, we'll grab the position from the input, and if we substitute this socket out, you'll see that instead of making this check against the tile and all of the elements in the tile, we're now making against the individual geometry elements, so everything that composes the copper versus the actual whole tile itself. So by using the attribute from earlier on, then we can actually capture just the individual tile and light up the whole thing. You can also see that if we come down here, I've set up the cursor to ignore the Z factor. So it doesn't matter if you move the cursor up or down, below or above the plane of the periodic table, it's only going to pay attention to the X and Y location. One key thing about this is that it requires the table to be in the positive quadrant of the X and Y axes. So if we come into, let's say, a wireframe view, you can see that the whole table is positioned above X equals 0 and to the right of Y equals 0. So it all has to be up here. And that's an important little note about using this with the asset browser. So I'm very quickly going to switch to a new scene, import this through the asset browser, and you'll see how you have to do things to set this up to make it work. In a new scene from here, I can grab my periodic table in the asset browser and drag it into the scene. You'll notice that the whole frame is set up so that I could put it in the right place right away, but I'm going to start by putting it in the center. I'll move this out of the way, and I will move all of the data objects to a new collection so I can hide them. Now, if I were to come into a top view and into rendered view, let's go ahead, stay in Eevee, and we'll turn on bloom so we can see the cursor. I'm going to grab it, I'm going to move into place, and you can see nothing is happening. It's not actually illuminating anything. And the reason for this is because of the way this is set up to work, the periodic table has to be in this upper quadrant. So let's go ahead, move it into place, just like that. If we come and grab the cursor now, move it over, everything is now working. So you can see if I move it over the elements as intended, it should work, but you have to have the periodic table in this quadrant. There are ways to account for this in the math. I did not program it in because it's, again, more of a teaching example than it is meant to be a useful tool. If you want to implement something like this yourself, you have to take into account the vector space. So if you're going to be dealing with negative or positive vectors, you might want to use absolute value to make sure you're always comparing against equal things. In some cases, you may want to check a value for a specific piece of data, or you might want to change that value. If we come in and we look at all the values through the periodic table, the easiest way to check values is very simply to come to the geometry nodes editor and just scroll across and see what the actual value is, and then follow the index plus 1 for that specific element. So hydrogen is 0 based on the index, and helium is 1, etc. So the atomic number is 1 offset from the actual index. And you can just simply find the value that you're looking for in the table and modify that, or rather check that. You cannot modify in this case. To modify, we're going to have to change the individual data object. And the easiest way to do that is by coming to the periodic table values, making everything visible so you can actually select it. And then let's say that we want to change something specific. So I would like to change the year that hydrogen was discovered because it wasn't actually 1766. This is a typo, hypothetically. So I'm going to make that object something that I can select. I'm going to grab it. And I'm also going to uncheck this little pin here so I can very specifically add a new geometry nodes tree here. You can see with my year object or my data, year discovered object selected, these are the Y values. And if I were to tab into edit mode, it might not be easy for me to grab the hydrogen value because it might be out of range of Blender's sort of top view box select. You can see even as I'm dragging, it's not giving me anything. If I come to wire view, still nothing. Partially that's because the object's down here, but it's also not going to let me grab it. So to correct for this, I need to be able to modify this. So I'm going to actually use a geometry nodes tree on the data object. I'll create a new tree. We'll scroll out to find that. Here it is. Set position, put it in here. And I need to select based on the index value of hydrogen. So index equals to 1. So we're going to use a compare integer. In the top socket, we'll use index. We'll say index equal to 0, because that is the hydrogen value. And then we're actually going to change the Z value. I need to change the original position, and so we're going to come drag out here, combine XYZ. We're going to use the original position XYZ, so I'm actually going to create another value here for separate XYZ X. Drag this out again to create the position. So I'm going to use the original X and Y position just so I don't move those. Now I'm going to change the Z value to what I want, and so I believe I said 1950. You can see that in the top of the spreadsheet that has changed. So if I want to make sure this is applied and reflected in the original table, then I very simply come to the geometry nodes object and I would apply that object. So we'll tab back into object mode, come here, apply this, and now my data has been updated. If I come back to my original periodic table, we go to the year discovered. You can see that the value for hydrogen has now been updated. And that is an approach that you can use for changing the individual data points of essentially any data object if you need to because there's a typo or because you want to update something that you've added in after the fact. To conclude, I want to give a brief overview of how I created this animation that has all of the neutrons, protons, and electrons for every individual element overlaid on the periodic table and nicely spinning. This is an updated version of the one that I posted earlier, so it actually loops pretty seamlessly, and I'll put an independently rendered clip of this somewhere for people who just want to stare at it. I'm going to preempt any of this description by saying that I'm not going to go into full detail here. This is very complex, and it would essentially probably double the tutorial length if I did. But the other thing is that this is not an accurate model. It is not suitable for teaching. So I want to really provide that as a clear disclaimer. This is not an educational tool. It was a technical exercise to see if this could be done in Blender. It can be done. And one of the things that I've learned through this is that it could almost definitely be corrected to accommodate some of the older models such as alpha for proper electron filling. Right now, the number of electrons in each ring is not necessarily correct below a certain point. And the idea that these blue ones are all valence electrons is also really not accurate. So I want to emphasize that. The thing that is correct here is the number of neutrons, protons, and electrons for every individual element. And I would like to emphasize how this can be achieved technically so that you could expand on it if you wanted to. I've also been asked at various points if I'd given consideration to pursuing some of the more quantum mechanical demonstrations of orbitals. I've thought about it. It's very complex. We're going to see just how complex it was to create this. And so it might take some time to get there. It is something that has my interest, but if I don't have the time, then I might not get around to it in the near future. Let's go over to the Geometry Nodes tab and break down some of this. The first thing worth noting is that this looks deceivingly simple. It's very similar to what we've seen throughout this tutorial. In fact, I'm going to enable this little switch right here because that's going to let us see the periodic table underneath at the same time. So now we have the individual elements on top of their data on the periodic table. And what we've done is basically the same thing that we did for many of the other scenes, such as when we put small spheres on. We took the 118 table positions and we created a series of controls to place something on top of that, namely, in this case, the right number of protons, neutrons, and electrons. For the electrons, we're going to look at them first and very, very briefly. I essentially created a large series of nodes here that looks at where the atomic number is, and then it says, based on that, which row it's in, what column it's in, and just using some of the math of the electrons, it creates a ring. Now, the way that it does that is a little bit more detailed than I want to get into, but it separates out the valence and the core, as I've called them, electrons. And if we were to open one of these nodes, you can see each of these has its own level. A lot of this is what I would consider harder coding, so it's really meant to work once. It's not super adaptable, but the rough idea is that for each of these, if we come back to frame 0, basically you want to go in and you want to create a circle that has a certain number of points. Every initial circle has a resolution of 32, which basically makes it look nice and smooth. I'm going to create one of those circles over every single one of these points. And when I do that, later down the line, I'm going to resample that curve to have only the number of points that I need to convert into points so that I can instance a sphere, namely the electron. So for this one, it starts off having 32 points, but I don't want to put 32 electrons here. I only want to put 8. And so as I come further down, I'm going to resample that. In fact, I have a count here that is somewhere over here and is basically just doing some math to calculate which row it's in so that it knows to put the right number on there. It resamples and then I can place everything. And so this is something that is similarly expressed in the creation of the nuclei, which I think is actually a little bit more informative. And so we're going to go back. I will note that this is available for free on Gumroad for people who want to explore it or take a little bit more of an in-depth look at how I went about creating this. For now, let's go look at the atomic nuclei. So zooming in here, you can see that most of the nuclei creation is pretty simple. I'm going to instance on points some UV spheres. I'm going to translate those to move them up above the plane of the actual tile. And then I'm going to set the material. I've created special materials for each of these protons, neutrons. These do some fancy things as well. That all gets joined together, and then it goes out to create this. But the important or the key thing that I'm pleased with here is that each of these is actually correct in terms of the number. So let's go to something a little bit easier to see, such as helium. Helium has an atomic weight or atomic mass of 4 and an atomic number of 2. So it should have 2 neutrons, which you can see 2 little black spheres there, and 2 protons. You can see one here, and if we were to change the angle a little bit, you'd be able to see the other one kind of sticking out. So it's a little hard because everything is a little too dark, so we'll bring that up just a little bit. 2 spheres overlapping each other, and also 2 other spheres for the neutrons. And so all of this is being calculated for every single atom or every single element on this table accurately. I want to focus on fluorine because it's a good example of how to use this math and also of the underlying logic here. So fluorine is unique in, well, not unique, but it is convenient as a teaching example because it has 10 neutrons and 9 protons. And so when we come in here to create atomic nuclei, we open this up, we see at the beginning, we're taking in all the table positions. The challenge here is that I need a way to be able to put multiple objects on a single point. And normally I could just do that with a nice instance on points, but I need to be able to pull information from the underlying position. So this position on the periodic table, the one for fluorine, contains a ton of information about fluorine itself. It has the atomic number, it has the atomic mass, it has the year discovered, it has all kinds of things that I want to be able to use. And I'm not going to be able to use that right away to create multiple objects. To do that, I have to do a little bit of transferring of attributes, and also I have to think about how I'm going to make this work. So for starters, I'm going to create an instance on points. Namely, I'm going to instance a curve line on top of each of these positions, every single one. But specifically for fluorine, I'm going to create a curve line right here. And every curve line in Blender starts with 2 points, a start and an end. Curves have a nice feature in Blender where I can resample them. I already talked about this with the electrons, but what that means is that I can resample the curve to create a number of points. For fluorine, I want 9 for the number of protons. I'm going to pull that number 9 from the atomic number. And so what I need to do is I need to first instance a line, realize that instance to make it an actual piece of geometry I can manipulate, and then I'm going to resample that curve. So instead of having 2 points, it has 9 points for fluorine. I'm going to get that information from the atomic number, which I am transferring in based on the proximity, because it's right here, of the original 118 points. Then I can convert all 9 of those nice points from a curve into a series of points, and I can set their position. So in this case, I am setting the position on the basis of the original position. So it's just going to match where it was in space. It's going to stay on top of the fluorine tile, basically. And then from there, I'm going to use another set position with an offset. And this offset is going to essentially generate spherical coordinates based on X, Y, Z. And I believe this also pulls in the atomic radius, so you could use that for scale as well. This is all just math to essentially create spherical coordinates. And what that means is that if I didn't have this, this would look very boxy. And instead, it kind of roughly throws this out to look like a sphere. The neutrons are doing the exact same thing, but in this case, we have a very small bit of simple math here, where we're actually taking the atomic weight and we're subtracting out the atomic number. Again, we have to transfer that attribute onto this piece of geometry based on the proximity. The proximity is perfect because it's right over top the actual element. And if this is a little bit too complex, I don't blame you. This is a very complex concept. I'll link another series of Arundel videos below because they are really the best at explaining this that I've encountered personally. But all of this comes together to finally create the proton cloud and the neutron cloud for every single one of these elements. It's a very nice way to be able to create multiple objects on a single point using curves. So all of this comes out, you instance all these points, join everything together, join it with all the electrons, which are similarly complex, and combine all this into the final product. And through some nice animation controls, you can loop this seamlessly and the whole thing spins. Again, I really want to emphasize as I close this off that this is not an accurate model. Please do not use this for teaching. Unless you're teaching geometry nodes, in which case it's probably a great example of that. But I will likely revisit this in the future. Otherwise, please enjoy this. It is available for free, both the table and this specific demonstration example, if you want to dive more into this. To wrap up, I want to start with a huge thank you to my supporters on Patreon who really helped make this possible. This has been the largest project I've undertaken to date, and I'm still planning to build this to be more practical, useful, and just fun. This tutorial/walkthrough has been one of the more difficult to plan because there are so many potential lessons in this case study. I hope some of the examples that I've covered here have helped make this asset more accessible, provided some useful lessons about geometry nodes, and inspired people to make more data-driven Blender projects. If you found this video useful, consider subscribing or sharing it with your friends and colleagues. I want to emphasize again that the periodic table asset, including the looping element animation version, are available for free on Gumroad. If you end up using this asset for something, consider tagging me on Twitter at cgfigures. I'd love to see how people put this into practice. If you have questions about this tutorial, a specific question, or the asset itself, feel free to leave it in the comments here or jump on over to the blender.science community Discord for support, which I've linked in the description. On a personal note, this has been a very rewarding project. I've had many people reach out to me about how this just seems useful and cool. In some way, I think it captures a little bit of the magic of chemistry, and it's certainly a reminder for me of why many of us love the subject. So as always, thanks for coming out, and until next time, you have yourselves a great old day.